asking you to do. Alright? So one question is out. Okay. This is the 47th lecture, and our discussion is on the topic of widebanding by overall feedback and dual loop feedback. Overall feedback, as I have told you, the number of stages is usually restricted to 2 or 3. If it is 2, then the circuit is called feedback pair, and if it is 3, then it is called a feedback triple. Two examples of feedback pairs we had discussed very briefly. I shall draw the circuits again. One is the series shunt. That is, you have a two-stage amplifier. I am not showing the DC biasing. You have a two-stage amplifier. DC biasing is not being shown, so the loads are grounded, and it's a series shunt. Series shunt means we should have this. We should have an unbypassed emitter resistance here, R sub E, and this is my source. This is my source, and the next stage can be common emitter. The output of this is fed to the input of the second stage, Q1, Q2, and this, since this is series shunt, the shunt connection comes from here and goes to the unbypassed emitter resistance in series with a resistance RF. That the feedback is negative should be obvious. Why? Because the voltage applied here is the input voltage Vs, source voltage, minus the voltage developed across this. Now this voltage well, I think you can see from here to here there is a phase shift of 180 degrees. From here to here, is there a phase shift between the voltages? What about the currents? Current and voltage, they are in phase. Okay, so the overall feedback is negative. You satisfy yourself that the overall feedback is negative. The input impedance is large because it's a series connection. R sub I is large, and R sub O looking back from RL2 would be low because of shunt connection, and therefore this is a circuit suitable for voltage amplification. Low input impedance, high input impedance, low output impedance, voltage amplification, and the voltage amplification mid-band value can be shown as approximately 1 plus RF by RE. The exercises that you should carry out are to find the mid-band values of RI and R0, and also output impedance and also FH. Obviously, it's not a trivial circuit. Miller effect, Miller simplification cannot be done for Q1. Why? Because there is a RE. Okay, but Miller simplification obviously can be done for Q2. All right, it can be done for Q2. Do that. But here you have to keep C mu as it is. But you will see that one or the other time constant will dominate. Okay. That part of the exercise is left to you. The second circuit, which we had also briefly drawn the other day, is a shunt series. Shunt series, and it's simply the dual of the series shunt. The circuit is like this: RL1, this goes to the next stage, Q2 RL2. It's a shunt series, and therefore if the source is here, and the source now should be current source I sub S, because it's a shunt series. The shunt connection will be from here, and the output connection is series, and therefore I should take a voltage across an unbypassed emitter resistance RE the voltage across this will be proportional to the load current. That is how it is series, and the feedback is through a resistance R sub F. As I said, R sub I would be low for this, R sub O would be high, and therefore it is a current to current transducer, and the amplification factor approximately, the mid band amplification is the same as in the previous case, RF by RE. Again, you can carry the same exercise, find the RI, find R naught, and find FH. Now, because of our obsession with voltage signals, most of our processing is through voltage. We shall at the fag end of the class, we will see, not this class, but later, we will see that current processing avoids most of the limitations on widebanding, current processing. Nevertheless, because of historical reasons, we have always thought of signals as voltage signals, although current processing is fast coming into the picture. It is not yet fully developed, but if you can compare the same transistors, Q1 and Q2, same transistors, the series shunt and the shunt series combinations, you might find that the shunt series, that is this current processing, has a higher bandwidth than the voltage processing. Okay. Nevertheless, since this is the circuit that is mostly used, in order to make this in order to isolate the load from the transistor, from the feedback circuit more effectively, one usually adds a third stage here, which is a common collector stage. Okay. And the total circuit then becomes as follows. We have a Q1, this is the series shunt with a buffer, and therefore you require 3 transistors. It is not exactly a feedback pair, it will be a feedback triple, but the third transistor acts simply as a common collector. So we have RL1, this is Q1, the output is fed to Q2. Now Q2 is grounded, RL2, this is grounded. This output is from here, is taken to Q3, which is a common collector stage, okay, and the feedback is derived from the unbypassed emitter of Q3. It is a common collector stage, so the output voltage is here, and this is your voltage V0. The feedback is applied through a resistance from the unbypassed emitter of Q3 to the unbypassed emitter of Q1. Call this RE1 and this is RE3, and there is simply a resistance RF connected here. The source should be a voltage source, Vs. It is a voltage to voltage amplification. If you compare this with the previous circuit, that is the 2-stage overall feedback or a feedback pair, all that has been added is, you see, all that has been added is, instead of taking the output from, no, this is not the circuit, series shunt, this is the circuit, okay, this is the circuit. All that has been added is, instead of taking the output from here, output has been taken from that of a common collector stage. Another common collector stage has been added. What do you think will happen to the gain of this stage, the mid-band gain? It should remain the same, because it is a voltage to voltage, and the gain of the third stage AV3 is approximately equal to 1. However, the third stage does contribute a couple of poles. Isn't that right? This contributes a couple of poles. One is due to C pi and the other is due to C mu. However, there is no Miller multiplication. Why not? Because the Miller effect, C mu is from here to here, which is grounded. Alright. So, it does not harm FH as badly as it would have if there was a load here. And if you add a load here, what do you think will happen? If you add a load here, that is, if you add an RL3 here, gain will increase. The bandwidth decreases. This precisely is the circuit of the so-called feedback triple. If RL3 is absent, if RL3 is 0, then it is a feedback pair with a common collector output. If RL3 is not equal to 0, then this is a feedback triple. You can see that the overall feedback is negative, and all the three stages take part in amplification. So it's called a feedback. This is a three-stage amplifier. The feedback is from is it a series? Is it still series shunt? Yes, of course, because the voltage across RE3 is proportional to the load current. Okay, so this is the series shunt and feedback triple, and approximate expression for the midband gain AV is equal to minus RL3, not RL1 or RL2. RL1 and RL2 approximately do not take part in fixing the gain. The gain is almost determined by RL3 and the three components of the feedback network, that is RE3, RE1 and RF. Can you guess the underlying assumption? Under what condition will that be true? The betas are large. That's the only assumption. Okay, and the approximate expression is RE1 plus RE3 plus RF divided by RE1 multiplied by RE3. This is approximately the gain of this stage. And you see, the gain can be made independent of RL1 and RL2. It is determined by the external three resistances which form the feedback and the load of the third stage. You must understand the difference between a feedback triple and a feedback pair with a common collector stage. The two circuits behave differently, and the only distinguishing feature, only differentiating feature is the existence of an RL3 or non-existence of an RL3. But it affects FH drastically. FH will be higher in the feedback triple or the feedback pair? Pair. Okay? Because there is a huge Miller effect. So the gain is determined by RL3, and therefore C mu 3 multiplied by 1 plus GM3 RL3 will be a large capacitance. All right. Nevertheless, a feedback triple is also available as a chip. The internal load resistances RL1 and RL2 usually are replaced by what? Current sources, that is active load, and RE1, RE3, RF, these are provided externally because they determine the gain. RL3, the collector of the Q3 is also brought out, and you can use a resistance which you want. Okay, so here also one can try and hopefully succeed in determining FH and the two resistances, the input and the output resistances. You see, the input resistance would be approximately, can you tell me what the input resistance here shall be? R by 1 plus beta plus RE1 parallel. That would be the input resistance without feedback. That is the A circuit. It's not easy to guess it from the circuit itself. It is not easy to guess. You will have to draw the A circuit and the beta circuit and find it out. Okay. So you can find out Ri, you can find out R0. I can tell you that this will not be trivial, this will not be a trivial exercise unless you can figure out how to simplify this circuit, and that itself is is an interesting task. Now, there is something called dual loop feedback. That is, you remember that in local feedback, that is a single stage feedback, we had used either series or shunt. In a simple simple local feedback, we had either used series, which means an unbypassed emitter resistance. Series was useful as a voltage amplifier or current amplifier? Current to voltage or voltage to current? Voltage to current, okay. VS, RS. This is RL. And this is RE. Now, naturally the question arises, and in the shunt shunt, what we had done was to connect a resistance from here to here, and RE was equal to 0. All right. Now, in this case, Ri is high and R0 is also high. Isn't that right? Okay. On the other hand, in the shunt, Ri was low, Ro was also low. Now, in order to make a precise control of the input and output resistances, there is no harm in using a dual feedback. That is, use this as well as this and adjust the two feedbacks by adjusting two resistances or one resistance, such that the input resistance and the output resistance are exactly the values that you want. Now, a typical situation is in a power amplifier, where class A power amplifier, where you want to deliver the maximum available power to the load. You don't care for voltage amplification there, you don't care for current amplification. What you bother is that the power, maximum available power, should be transferred to the load. And there a precise control of R sub I and R sub O are needed, and this is often used. This is called a dual loop feedback. Dual loop feedback can be through a single transistor, can also be through two transistors connected in the cascade configuration. All right. It can be either this circuit, or it can also be a circuit in which Q is replaced by two transistors in cascade, one sitting upon the other. Well, the circuit would be like this: a transistor Q2 which sits upon a transistor Q1. This is the cascade connection. The overall load is here. One can easily guess why a cascade is used instead of a single transistor. Let me draw this circuit. Then the base of this is a common base circuit. The base of the second transistor, as is usually the case in a cascade connection, Q1, and the voltage source Vs, Rs. It's a dual loop feedback, so there is an Re, and the feedback resistance, the shunt connection, is from the collector of Q2 to the base of Q1. Okay, this is RF. You see that this is a dual loop feedback. One is through Re, the feedback is through Re. This gives rise to series, and this gives rise to shunt. Both are used in order to precisely control Ri and R0, because the major concern is neither voltage amplification nor current amplification, but maximum transfer of available power, transfer of maximum available power to the load. You can see why this circuit would be preferable as compared to the single transistor circuit for the usual reasons. Let us see if you recall. What are the reasons? The high frequency performance of this circuit, the cascade circuit, would be better than that of a single transistor circuit. This is always the case, because the C mu here will be reflected as 2 C mu, and the C mu here is grounded from base to, and therefore the Miller multiplication does not occur. Miller multiplication occurs, but very little in Q1, just doubling, and none in Q2, because that C mu is grounded. Therefore, this is a preferable circuit. Now, if you analyze the single transistor circuit, if you analyze the single transistor dual loop circuit, then the results, mid-band results, are as follows. Since we are talking of maximum transfer, maximum available power transfer, let us say Rs is equal to RL. Well, if that is so, if Rs is equal to RL, why didn't we connect RL directly to Rs? Maximum available power would have been transferred. Why did we introduce a transistor with a feedback? I am appealing to your common sense. Then the power, if Rs and RL were connected directly, who would supply the power? Only Vs? Only Vs. So Vs could be simply a microphone. It has no way to transfer power, to deliver power. And therefore you use a transistor amplifier in between, so that power is converted from DC to AC. Okay? That is the reason why the transistor amplifier is needed. Let Rs equal to RL, and let this be called equal to R. And let us also impose the condition that GMRE is much greater than 1, so that 1 plus GMRE can be replaced by GMRE. 1 plus GMRE occurs because of the feedback through unbypassed emitter resistance RE. Under this condition, the mid-band input impedance Ri is approximately given by RF RE, RF plus R. R is Rs and RL, both are equal, divided by RF RE plus RF R plus RER. This is approximately the input resistance mid-band, and the output resistance R0 is equal to RF plus R divided by 1 plus R by RE. Is this dimensionally valid, this expression?
Yes.
Yes, it is. So the denominator is dimensionless. Try to show that this is the case. In addition, if you desire maximum power to be transferred, not only from the supply to the load, but also from the source of signal, that is Vs, then obviously what you desire is that Ri should be equal to Rs. Okay. So, and let's have, and since RL is already equal to Rs, therefore the output resistance should also be equal to Rs. Alright. If that is so, that is, if in addition you require that Ri equal to R0 equal to R, then obviously no power is lost anywhere. You could not deliver more power than this. This is the ideal condition. And under this condition, this is the matched condition. You include here equal to Rs equal to RL. Alright. Under this condition, matched condition, the voltage gain S sub V, which is equal to V0 by Vi, is approximately equal to minus R parallel RF divided by Re. Very simple result. That is, the load resistance, the source resistance, each of them being equal to R, that parallels with the feedback resistance Rf and divides by Re. This is the voltage gain. Please do try to prove these results and also make an attempt to find FH. Now, this dual loop feedback using a single transistor, we said it could also be applied to the cascade connection. There is another way that it can be applied, and that is instead of a cascade, you use the cascade connection, all right, and apply the shunt connection and the series connection in a non-interactive fashion. It's not difficult to imagine how this is done. Let me draw this circuit. Two-stage dual loop circuit. Okay, the cascade connection is not a two-stage because one helps the other to reduce the Miller multiplication. But a two-stage means that there will be more amplification. Okay, and this circuit is as follows. You have the transistor Q1, some R sub C, which let us say is grounded. Then this goes to Q2. Q2 no longer sits upon it. Q2 is the second stage, and Q2 has the load RL. This is the final load. This is V0, and the the feedback is applied in a dual loop like this. This is RE2 and RE1. It's a slightly tricky circuit. I should not make a mistake. The shunt series connection is like this. From here, what we should have done is if it is a shunt feedback, you should have taken to the base of Q1. Instead of doing that, that's what I said, in a non-interactive fashion. The base, this voltage, what is the difference in phase between these two voltages? The base voltage and the emitter voltage. What is the difference? They are in phase, and therefore you could as well apply it here. This is one of the feedbacks, and this I will call as RF1. This is the shunt feedback, and the other one, the series feedback, is applied. The shunt series, the shunt series feedback is applied from here to this point. Okay, so this resistance is RF2. This is the dual loop feedback using two-stage. It can be shown that as compared to the cascade circuit, this circuit, because the two feedbacks are non-interactive, reduces the Miller effect. It can be shown, and it gives a higher gain bandwidth product. Not only it reduces the Miller effect, it also increases the gain because of two stages. So the GBW increases, and a practical matter is that the distortion in this circuit is lower than in the previous circuit. These are the two distinct advantages. But obviously you see the analysis and design of this circuit is much more complicated. At least you should try to do the mid-band analysis. Okay? And the results of mid-band analysis are as follows. Is the circuit clear? Is it clear that both are negative feedback?
So what happens to the overall bandwidth?
Pardon me?
What happens to the overall bandwidth?
Overall bandwidth increases as compared to the single transistor or the cascade circuit. That's how the gain also increases. Bandwidth also increases. as compared to the previous circuit. Okay?
Is that possible that both increase simultaneously?
As compared to the previous circuit, that is a single transistor circuit or a two transistor circuit, two of them in cascade. Okay? You see, in the cascade connection, the gain doesn't increase. What increases is FH, whereas here FH increases and also the gain as compared to the previous circuit. Now, is it obvious that both feedback are negative? This I have shown this is negative. What about this? Is this negative? Between this voltage and this voltage there is a phase shift of 180. Between this and this there is no phase shift, and therefore indeed it is negative feedback. Both apply negative feedback, and the purpose of dual loop feedback, I repeat, is to precisely control R sub I and R sub O. Now, if you make a midband analysis with the assumption that RS is equal to RL as in the previous case, if this is true, then R sub I is approximately equal to, please note these expressions and try to verify, RF2 plus RE2 RE1R divided by RE1R plus RE2 RF1 plus RE1 plus R. It's not a simple expression, one should do it, one should derive this carefully, and R0 is approximately RF1 plus RE1, very similar expression, only 2's are replaced by 1's. RE2R divided by RE1 RF2 plus RE2 plus R plus, can you tell me what this next expression? RE2R. And the voltage gain AV, which is V0 by Vi, is approximately equal to RF1 plus RE1 divided by RE1. I have written this intentionally. Tell me if there is any inconsistency in this expression. Are these dimensionally valid?
Yes, sir.
Dimensionally valid. Okay. How come? That is the question that should rise in your mind. How come this is independent of RF2 and RE2? Because it has been assumed that for this, we assume that Ri equal to R0 equal to R. That's how it only depends on RF1, RE1 and RE1. RF1 and RE1. What is the condition for these two to be equal? RE1 is equal to RE2 and RF1 equals to RF2. Okay? This is the condition. You should try to derive this. Finally, in this class, in the rest of the time that is left, we go back to the differential amplifier. We now show that the differential amplifier, which we have discussed very elaborately, can be used as a wideband amplifier. And one of the circuits, I don't remember in which minor I gave this circuit, in which the differential amplifier had the modification that one of the transistors didn't have any load in the collector. Second one. Okay. That circuit I had used intentionally there because that circuit is a very popular circuit as a wideband amplifier without affecting the CMRR or the gain. It becomes a wideband amplifier. Let me draw this circuit, then I will explain why it is wideband. The circuit is VS-RS. It's a single-ended circuit. That is, input is applied. It is not used to amplify the difference between two voltages. It is used to amplify a voltage, okay, but two transistors are used in the differential connection. That is, the coupling is through emitter. Okay. So one of the transistors Q1 is a common collector. Okay. It goes directly to VCC. It doesn't have a load. The emitter comes here and is coupled to the transistor Q2 emitter, and the common point is biased. The bias is by forcing a constant current, a current generated from the common emitter to the negative supply of whatever it is, the ground. This has a load. Let's call this R sub C. This goes to plus VCC, and the output is taken from here. What do you think this base should go to? Where should it go to? Ground. Okay. And the output is taken from here to ground. This is a very popular circuit as a wideband voltage amplifier. Okay. It is not a differential amplifier in that sense, but the differential configuration has been used to make it wideband, and the reasons are not difficult to imagine. Why it is wideband? Why it is wideband is because this is a common collector, and therefore C mu from here to here does not cause Miller multiplication. Similarly, here from here to ground, once again it is grounded. So both C mu's, their teeth have been taken off, so they can't bite. Okay, they can't harm this circuit. Now let's see the analysis of this is also gives also very elegant results. Analysis can be done in a very simple manner. One requires an equivalence circuit, which we shall now draw carefully. The equivalence circuit is as follows: Vs Rs, this is the source. Then let's put these points B1, C1, B2, C2, and the emitter is common, and therefore let's have an emitter line here, which is E1 on the left and E2 on the right. This will help us in drawing this circuit very easily. From B1 to E1, what do you have? You have an R pi and a C pi. Okay, the transistors are identically biased, and therefore all parameters are equal. Okay, so we will draw R pi and C pi in a little different manner. Can you guess why? I want to call this combination as an impedance Z pi. Okay, R pi C pi. In a similar manner, from B2 to E1 we have another R pi and C pi, identical impedances. Now the V pi 1 and V pi 2 would be like this. This would be V pi 1 with this polarity plus minus, and V pi 2 would be from B2 to E1 with this plus and this minus. Don't make a mistake now. Okay, V pi 1 and V pi 2 polarities are as shown. Don't make a mistake. V pi polarity is positive at the base and negative at the emitter. Okay, is this okay?
Yes, sir.
From B1 to C1 we have the C mu, and C1 is grounded. From B2 to C2 we have again C mu. However, C2 is not grounded. It goes to ground via R sub C. And this is the voltage V0, output voltage V0. Now, what do we have from C1 to E1? We have is the polarity correct? From the collector to emitter is GM V pi 1, and this would be another from C2 to E2, another current generator with this polarity, right? which is Gm times V pi 2. The circuit is complete. E2?
Base.
B2 is grounded, yes. B2 is grounded. Anything else left? Now, look what happens. Let us write a KCL at this common point, E1 and E2. Let E1 equal to E2 equal to E. Let us write KCL at E. E2? Not at all. It's a current source, infinite impedance, and therefore it's open. This is E1, E2. This is a current source. It's not grounded. We are not considering the differential mode. There is no differential mode. Is that right? It's being used as a single-ended amplifier. One source, one voltage source. Okay. If I write a KCL at the node E, then I have to take care of one source is V pi 1 divided by Z pi. Okay. This is a current coming in. The other current coming in is V pi 2 divided by Z pi. So plus V pi 2 divided by Z pi. Alright. This is one current. This is another current. Then I have these two currents. Gm V pi 1 and Gm V pi 2. So Gm V pi 1 plus Gm V pi 2. Alright. And this should be equal to 0. What is the natural conclusion?
V pi 1 equal to V pi 2 equal to 0.
No. If that would have been the case, there would have been no amplifier. V pi 1 should be equal to minus V pi 2, which means that the circuit is now tremendously simplified. You see, you could have, this is Z pi, this is Z pi, and there is a V pi 1 here, there is a V pi 1 here, plus minus. Is that clear? So what you have is twice Z pi, they come in series. Why? Because Gm V pi 1 is equal to minus V pi 2. So Gm V pi 1 comes here and it goes out like this. Therefore, this connection can as well be forgotten. You see what I mean? Now, what is the simplification? Let's look at the simplification. The simplified equivalence circuit. Not only that, if this connection is removed, then C mu can come across RC. Okay? So the circuit becomes easier to look at. And this C mu, where does that come? It comes from here to ground. Okay? So, what we have is the following, the simplified equivalence circuit. We have a Vs, Rs, then we have a, now let's look at the components, let's draw the components. Twice R pi plus R pi in parallel with twice C pi, C pi by 2. Not only that C mu also comes in parallel, and therefore C pi by 2 plus C mu. Is that clear? C pi and C pi in series. So the effective value is C pi by 2, and then C mu comes in parallel. What is the voltage now? Twice V pi. We don't have to say V pi. Okay, V pi 1 is V pi. What was your question? Which C mu is this? This C mu. From B1 to C1. C1 is grounded, and therefore it comes from B1 to ground. Okay? Alright. So this is my twice V pi, and then in the output circuit we have the GMV. In the output circuit, which GMV do we consider? We have to find out V0, and therefore it is this GMV. Okay? GMV pi 1, which comes to C2. Alright? It comes from ground to C2. Alright? So from ground to C2. GMV pi, this is C2, and C2 has two two other components, R sub C, the load, and the C mu. You see how simple the circuit has become, and this voltage is V0. Analysis of this circuit is extremely simple. You can easily see that the mid-band gain AV0, can you tell me what the mid-band gain would be? First from here, minus GM RC, and then 2R pi divided by RS plus 2R pi. We have made a mistake. Half of this. So this 2R pi should go. Is that clear? Why half? Because this is GMV pi. This is not twice GMV pi. Right?
Plus
GMRC. Wonderful. Yes, this is plus GMRC. So this is simply beta RC divided by RS plus 2R pi. This is the mid-band gain. And what are the pole frequencies? Omega P1 would be 1 by 2R pi
C pi by 2 plus 6
C pi by 2 plus C mu. I heard a murmur parallel something?
2R pi parallel RS.
That is correct. 2R pi should parallel RS. Quite so. And omega P2 should be equal to 1 by RC times C mu. And therefore, I didn't make I didn't write any more equations. I did this by inspection. I found out omega P1, omega P2. Can you now write down the expression for AV? That is Vs by V0 would be equal to AV0 multiplied by 1 plus, yes, J omega by omega P1 multiplied by 1 plus J omega by omega P2. And pardon me? V0 by Vs, yes, not the other way around, yes, V0 by Vs. And therefore, you can now find out omega H by any of the techniques that you have learned. Since it's a quadratic only, it's not difficult to solve for it analytically, exactly. If you don't like it, then you use 1 by omega H equal to 1 by omega P1 plus 1 over omega P2. Okay? The third is this. You can find it out by 3 different methods. One is analytical. This is also correct. This is the method of short circuit time constant. Short or open? Open circuit. Don't let me make a mistake. And this is the expression, approximation derived from the exact expression. Okay? We shall, next time, we shall take an example and compare these 3 figures and see which one is more correct.